Okay, so our second speaker today is Dimitrios Ntalampekos, and he will talk about quasi-conformal characterization of Schottky sets. So please, Dimitrios.
Thank you very much for the invitation. So yes, I will talk about the characterization of Schottky sets. First, let me give the basic definitions. What is a Schottky set? We see one in the picture. So a Schottky set is the complement in the sphere of a finite or countable collection of disks. The disks must be geometric open disks, so the spherical radius is less than pi, okay, so that they don't cover the whole sphere. And the closures are either disjoint or they could contain one point. Okay, so we just exclude the situation where we have two disks that have exactly the same boundary. This is the only case that we exclude. Now, where do we see Schottky sets? First, they appear as round Sierpinski carpets. What is a carpet? It's a set that is homeomorphic to the standard carpet, which is constructed by squares. So these sets have empty interior, and the complementary components in that case have disjoint closures. Now, another instance where we see Schottky sets is circle domains. So circle domains appear in complex analysis. They are connected open sets in the sphere whose complementary components are points or disks. If we take the closure, then we have a Schottky set. The interior here is non-empty, and the complementary components must have disjoint closures. Now, we also see Schottky sets in dynamics. So they appear as limit sets of Kleinian groups. This is the Apollonian gasket. So again, we have empty interior, but in that case, the complementary components can touch. So we see here the disks have points in common, the circles maybe. All right, so we are interested in the so-called uniformization problem for Schottky sets. So we want to understand when we can transform a given compact set to a Schottky set with a well-behaved map. And if we can do this, what can we say about uniqueness? So we are interested in doing this because Schottky sets enjoy some very strong geometric and analytic properties. They also have rigidity properties. So they can help us study the given set in a better way. So first we have to figure out what's the right type of map. We want to find a well-behaved map. The best type of map we can hope for in this setting is bi-ellipsis maps. However, bi-ellipsis maps are impossible in general, even when we have very nice geometry. So here's a simple example. There exist self-similar square carpets that have house of dimension arbitrarily close to 1. So it cannot be equal to 1 if they are self-similar, like this one, but it will be arbitrarily close to 1. But on the other hand, the Schottky sets have house of dimension bigger than 1.03. This was proved by Larban. Since bi-ellipsis maps preserve the house of dimension, it's clear that we cannot transform those square carpets that have dimension close to 1 to round carpets or to Schottky sets. Conjecturally, here the optimal bound is 1.30568, which is the dimension of the Apollonian gasket. This is an open problem.
Has there been any progress on the bound since 1967?
No, as far as I know, well, there might be actually better bounds. I studied this problem in some joint work with a student. I think we got some other bound. It might be a bit better, but I didn't check the. Maybe we got it to 1.08 or something like this. But of course, the techniques that we use will never get the actual the best bound. All right, so the next type of map to look for is, of course, quasiconformal maps. I know I don't have to give the definition in the Quasiworld seminar, but okay, let's just give a slide. So a homeomorphism between open subsets of the sphere is quasiconformal if it maps infinitesimal balls to infinitesimal Jordan regions that have bounded eccentricity, in the sense that we can find two concentric balls. One is contained in the image and the other contains the image, and the ratio of the radii is uniformly bounded from above by a constant that does not depend on x or on r. So this is the metric definition of quasi-conformal maps. Now, if this phenomenon occurs at every scale and not just at infinitesimal scale, then the map F is quasi-symmetric. So quasi-symmetric maps are stronger than quasi-conformal maps. But if the domain of the map is the entire sphere, then quasi-conformal maps and quasi-symmetric are the same. So let me mention some early results about the uniformization by Schottky sets. So in 1990, Macmullen proved that if the limit set of a convex co-compact Kleinian group is a carpet, then it is actually quasi-conformal equivalent to a round carpet. Now, the same year, Heron and Koskela proved that if we have a uniform domain, then it is quasi-conformal equivalent to a circle domain. Uniform domains are domains in the sphere that share common geometric features with the unit disk from a geometric and also hyperbolic geometric point of view. Now, let me point out that in this talk, when I say quasi-conformal maps, most of the time we refer to maps defined in the entire sphere. Okay, there's a related problem, which is Koebe's conjecture. It asks if we can map a domain in the sphere conformally to a circle domain. But in that problem, the maps are defined only in the domain. So they don't have a nice behavior as we approach the boundary. Instead, our maps are defined in the entire sphere. So they have nice behavior at the boundary of a domain, at the complement as well. Okay, so this is something to keep in mind. So we're not going to talk about problems of this type today. Now, 20 years after these two results, I think the next result in this area was by Mario, 2011. And he proved that if we have a Sierpinski carpet whose peripheral disks, these are the holes of the carpet, if the holes are uniform quasi-disks and they are uniformly relatively separated, I'm going to explain these assumptions, then we can map the carpet quasi-conformally to a Schottky set, to a round carpet. Now, what is a quasi-disk? It is the quasi-conformal image of the unit disk. Again, the map is defined in the entire sphere. The most famous quasi-disk perhaps is the region bounded by the von Koch snowflake. And an equivalent definition of a quasi-disk is that the boundary curve has no cusps. Now, the second condition, it's a bit harder to define. So for two regions UI, UJ, these are the holes of the carpet, we define the relative distance to be the ratio of the distance divided by the smallest of the two diameters. And we require that this is uniformly bounded from below. And here one can use Euclidean or spherical metric. It doesn't make a difference. Maybe this will be changed by a constant. So the uniform relative separation condition says that if, for example, UJ is smaller than UI, then the distance between them must be at least delta times the diameter of UJ. So this condition prevents large peripheral disks from being very, very close to each other. Now let's make some remarks on this theorem. First, Mario uses the transboundary modulus of Schramm, which was invented in 1994. It was a very important tool in complex analysis. Since then, it has been used in numerous works. Of course, this was not available at the time of Macmullen and Heron and Koskela. Also, Mario obtains a uniqueness statement for carpets of area 0. And actually, the uniqueness follows from some earlier work of Mario, Bruce Kleiner, and Sergei Merenkov. And it turns out that uniqueness relies crucially on the geometry of disks. It's an argument involving reflections. On the other hand, the existence part of the theorem of Mario does not rely on the geometry of disks so crucially. It would work if we wanted to convert a carpet to a square carpet, or a carpet whose holes are equilateral triangles, for example. So it doesn't use any strong geometric feature of the disks. Now, regarding the assumption of uniform quasi-disks, this is a necessary assumption. So if we want to convert a Jordan region to a disk with a quasi-conformal map, then it is a necessary condition that this Jordan region is a quasi-disk, of course. On the other hand, the other assumption, it's a bit more obscure, the uniform relative separation assumption. This is not a necessary assumption. One can easily construct a round carpet that does not satisfy this assumption. For example, even here, these two disks are very, very close to each other. So one can construct a sequence of such disks that get closer and closer to each other. So since my PhD thesis, I started studying the problem of removing this assumption of uniform relative separation. Can we remove it? And if we remove it, what happens? So the first easy observation is that if we want to convert a square carpet to a round carpet, then we cannot remove the assumption. It's actually a necessary and sufficient condition so that a square carpet can be mapped to a round carpet. And let me sketch the argument. It's pretty simple. So let's suppose that we have a square carpet that gets mapped with a quasi-conformal map to a round carpet, but the uniform relative separation condition is not true. So this means that there exist sequences of squares that are very big compared to the distance between them. Of course, there are other squares here. It's a square carpet, and here there are other disks. But we just focus on a sequence of pairs of squares that get very close to each other. Of course, there are other ways that the square Bn can approach the An. Maybe they can approach in this pattern, but let me just suppose that corners approach each other. So one has to take cases. We can rescale the square Bn so that it becomes the unit square, and we can rescale this disk so that it becomes the unit disk. And this scaling procedure will give a sequence of quasi-conformal maps. So we can pass to a limit, and this way we'll get a limiting quasi-conformal map that maps the unit square to the unit disk, and it maps a quarter plane to a half plane that's tangent to the unit disk. And therefore, this map takes this 90-degree angle and maps it to a cusp, and this is not allowed by a quasi-conformal map. All right, so if we want to have a quasi-conformal uniformization, we cannot remove this assumption. Well, in my thesis, I proved another result. I removed this assumption, actually, and I got another uniformization result. So suppose that we have a Sierpinski carpet of area 0, and for the peripheral disks, we assume that they are alphas 2 regular. So let me remind you, it means that if UI is a peripheral disk and we intersect it with a ball of radius r, then the area must be comparable to r squared, because x has to lie in UI and r has to be small. So we assume that they're alphas 2 regular. This condition holds for quasi-disks. And second, we assume that they are quasi-round. So like before, we can find two concentric disks. One is contained in UI, the other contains UI, and the ratio of the radii is uniformly bounded from above. And this is another condition that holds for quasi-disks. So these two conditions are strictly weaker than being a quasi-disk. Then the conclusion, of course, here I should put uniformly regular and uniformly quasi-round. This is something I omitted. The conclusion is that the carpet can be mapped to a square carpet with a map that's carpet quasi-conformal. So this is a generalization of quasi-conformal maps. The map is not quasi-conformal in the classical genuine sense. but in a generalized sense. So these maps are defined by quasi-preservation of a notion of transboundary modulus, but I'm not going to define them here. And we see that we have dropped entirely the uniform relative separation assumption, and also we have weakened the quasi-disk assumption. Now, in the next years, I kept studying this problem, and I was able to remove entirely the geometric assumptions and replace them with something much weaker. So if we have a carpet, and we just assume that the peripheral disks have diameters that are square summable, no other uniform geometric condition, then we can find what I call a packing quasi-conformal map from a Schottky set onto S. This is another generalization of quasi-conformal maps. Unfortunately, these maps are not in general homeomorphisms, but they are just uniform limits of homeomorphisms. And the defining condition here is something very natural. We just assume some absolute continuity in almost every line, and also a distortion inequality that involves the Jacobian and the minimal upper gradient. So it's what one would expect. Now, what is the motivation behind this theorem and this condition? The motivation comes from probability theory, specifically from CLE. The conformal loop ensemble carpets are some random carpets that appear in the study of SLE, and it was proved by Rode and Vernes in unpublished work that the CLE carpets satisfy this condition. And actually, very recently, just a couple of months ago, Doherty and Miller uploaded to arXiv a preprint in which they give a complete proof of this condition. But with probability 1, this condition is satisfied for the random carpets. So as a corollary, we can get that the CLE carpets can be uniformized by Schottky sets. Of course, now there are many other further questions that are raised. One would want this map to be a homeomorphism. Also, there's a question of uniqueness, but I think they can be attacked by probabilists rather than an analyst. Now let's get back to the initial problem. Okay, we want to quasi-conformally convert a set to a Schottky set. Okay, we don't want to leave the quasi-conformal world. So let's see an example from complex dynamics. So here we have a Julia set of a rational map. We have a very nice geometry, meaning that the Fatou components are uniform quasi-disks. So from one point of view, we have very nice geometry, but from the other point of view, we have touching Fatou components. So we do not have even separation. So we cannot talk about uniform relative separation here. So we studied the problem of uniformizing those Julia sets by Schottky sets in joint work with Yusheng Luo, and we were able to actually characterize those Julia sets. So if R is a rational map and the Julia set does not contain critical points, then the following are equivalent. The Julia set is quasi-conformal to a Schottky set. This is the uniformization. Next, we have the geometric criterion. The Julia set is a fat gasket, and this means that whenever two Fatou components touch, they're actually tangent to each other. There's a tangent line. And the third condition, which is a dynamical condition, is that every contact point is eventually mapped to a parabolic point of multiplicity 3. So we have a complete understanding of those Julia sets. The proof is purely dynamical, and unfortunately, there was no hope to extend this proof to general compact sets. Basically, one can show that there is a unique map, a unique homeomorphism from this Julia set to a Schottky set, and then the job that one has to do is to extend this to a quasi-conformal map of the sphere. So the homeomorphism is already given to us by some other work of Yusheng and his collaborators. Anyway, so after completing this work, for some months, I kept staring at this picture, and I made the following observation, that if we just look at the green Fatou components, forget about the red ones, the green ones seem to be uniformly relatively separated. any pair of them, they have a nice distance. They don't get too close to each other. And the same happens with the red ones. They're also uniformly relatively separated. So if we look at pairs of green or red components, everything is fine. Now, if we look at a green and the red component that's touched at a point, then we know that there's a certain dynamical condition. This is a parabolic point of multiplicity 3. So this actually allows us to convert these two components into two disks with a quasi-conformal map. So this says that this gave me the idea that we have to study the problem by looking at pairs of complementary components. So and this gave birth to the notion of pairwise circularizable regions. So two disjoint Jordan regions are called quasi-conformally circularizable if there exists a quasi-conformal map of the sphere that maps them into two disks, disjoint disks. And we want the boundaries to be distinct. We don't want to have a common boundary. And if we have a finite or countable collection of disjoint Jordan regions, then we call them uniformly, quasi-conformally, pairwise circularizable if every pair is K quasi-conformally circularizable for the same K. Okay, so we just studied the problem in pairs. And, well, now we can state the main theorem. The main theorem says that if we have a collection of disjoint Jordan regions in the sphere, the following are equivalent. The regions are uniformly, quasi-conformally, pairwise circularizable if and only if we can find a quasi-conformal map from the set S, that is the complement of the regions UI, onto a Schottky set. And moreover, this map is one quasi-conformal on the set S, meaning that the differential of F is the composition of a scaling with an orthogonal matrix. And moreover, this map is unique up to Mobius transformations, even if the set S has positive area. So now this theorem actually implies Mario's theorem, because there is an old result of Heron which says that if we have the uniform relative separation condition of Mario, it implies this quasi-conformal circularization assumption. So we can get, in this way, Mario's theorem. Now, I'm going to make some remarks about the theorem. The theorem gives a quasi-conformal homeomorphism of the sphere that maps the set S to a Schottky set. A priori, it's not even clear if there is a homeomorphism. So we do not have a topological characterization of Schottky sets. And this is an open problem to find a topological characterization. The assumption that we have, this circularization assumption C, gives some topological consequences. First, any two regions UI, UJ, the closures are either disjoint or they intersect at one point. Of course, since we can convert these two regions to two disks, this is clear. Now, second, this is more subtle. If we have any three Jordan regions, the closures, the intersection of three closures must be disjoint, must be empty. Okay, of course, if we look at disks, we cannot find three disks that are disjoint and the boundaries pass through the same point. So this is a natural condition. And the third topological consequence is that the diameters converge to zero. Okay, the UIs are uniform quasi-disks, they are disjoint, so the diameters have to converge to zero. So the question is if these three topological conditions are sufficient so that we can find a homeomorphism onto a Schottky set. It's an open problem. We only know the answer in the case that the closures are disjoint. This follows from Wyburn's criterion for Sierpinski carpets. But if the intersections are non-disjoint, then there's a lot of rigidity. There might be a unique homeomorphism onto a Schottky set. So it's a difficult problem. As I said, in the dynamical setting, there's a unique homeomorphism. while in the setting of carpets, there are infinitely many homeomorphisms between any two carpets. All right, and now the second question is how to find a necessary and sufficient geometric condition for the circularization assumption. Again, this is also a difficult problem to characterize find the quasi-conformal characterization of the tangency of two disks. So this is a problem that actually Mario assigned to me. It was the first problem in my PhD studies. I was not able to resolve it. All right, so in the remaining time, I'm going to talk about the proof of existence, which is the most interesting. So let's suppose that we have an infinite collection of disjoint Jordan regions that satisfy the condition C. And, well, the main idea is to find a quasi-conformal map of the sphere that maps the complement of finitely many of them onto a Schottky set. And if we can do this with uniform constants, then we can pass to the limits to get the map that's, that maps the entire set S onto a Schottky set. Now, there's an obstacle here, which is not present in other works. We cannot use Koeber's uniformization theorem directly. So Koeber's uniformization theorem says that if we have a finitely connected domain, we can conformally transform it to a finitely connected circle domain. Here, the regions UI might touch each other. So we cannot apply directly the theorem to convert these three regions to three disks. Okay? If we apply Koeber's theorem to this domain, then it would convert these three disks to a single disk. So we cannot do this. Now, how can we fix this? There is a way to fix this, which is not easy. We can prove that if we are given a finite collection of regions satisfying condition C, then we can modify them to obtain regions that satisfy the same condition and have disjoint closures. So roughly speaking, the picture looks like this. So we kind of modify the regions in the places where they touch, and then we have disjoint closures. Somehow this is not easy because one has to, it's not easy to keep the condition C because one has to account simultaneously for all the regions. We cannot just work in pairs. But anyway, once we do this, then we can apply Koeber's theorem, which says that we can find a conformal map from this unbounded domain onto a circle domain. Of course, this conformal map is not defined in the entire sphere. Our goal is to find maps defined in the entire sphere. So somehow we need to extend everywhere. And to do this, there's an intermediate step. So we first prove that the map F is uniformly quasi-symmetric. And this is actually the hardest part of the proof. Once we prove that this map is uniformly quasi-symmetric, then we can easily, with standard arguments, we can extend it to the whole sphere. We can use the well-known Berling-Alfors extension theorem. So in this way, we get a quasi-conformal map defined in the entire sphere. It maps our finitely connected set to a finitely connected circle domain. And if we normalize this map appropriately, we get equicontinuity. So we can take a subsequence that converges to a quasi-conformal map, and it maps the set S to a Schottky set. Okay, so these steps are standard. They have appeared in several works. The non-standard step is 2. So let's discuss in detail this step. We'll start from a toy version. How can I prove that a conformal or a quasi-conformal map is quasi-symmetric by using modulus? Let's suppose that we have a quasi-conformal map of the unit disk to illustrate the technique. We consider 2 disjoint continua in the disk, and we suppose that the relative distance is bounded from above. So this means that these continua are large and they are close to each other. Now we take the family of curves that connects those two continua. How large is this family? Well, there is a way to measure the size of the family by using the notion of modulus. So conformal modulus is an outer measure on curve families. So it says how big a curve family is. It turns out that if these continua E and F are very, very close to each other and they are large, then there are a lot of curves that connect them. And the modulus of the family of curves that connects those two continua is uniformly bounded from below. This property has a name. It's called the Loevner property of the plane or of the disk in that case. Now we apply the map F. So the map F is a homeomorphism. We take the images of the sets and we take the images of the curves. As I said before, conformal modulus is conformally invariant and it is quasi-conformally quasi-invariant. So if we take the modulus of the image of this curve family, then it's also bounded from below. And somehow now we want to derive from this that the relative distance of E prime and F prime is bounded from above. So we want to derive that the continua E prime and F prime are close to each other and they are large. This is in some sense the reverse of the Loevner property, but it follows from a certain modulus bound for annuli. So in the plane, we have this well-known modulus bound. If I have an annulus, and if I take the family of curves connecting the boundary components of the annulus, then the modulus is exactly equal to 2 pi log r over r to the negative 1. Now, since we are in the disk, if we take an annulus that looks like this, so we take just a part of the annulus, then the modulus is bounded from above by 2 pi times the logarithm. Now this, which I call the upper modulus bound, this is enough to give this implication. So the proof, well, summarizing what we have shown is that if the relative distance of E and F is bounded from above, then the images have the same property. The proof of this implication uses 3 ingredients. First, the Loevner property. Second, the quasi-conformal invariance of modulus. And third, an upper modulus bound for annuli. Now, once we have this implication, we can use a well-known criterion of Weissela, which implies that F is quasi-symmetric after we normalize it appropriately. There are some normalizations. I'm hiding a few details under the rug, but this is what we have to go for. All right, so in the case of the disk, everything works nicely. How can we apply the same argument now in a multiply connected domain? Okay, because this is what we have. Well, the idea simply fails when we have a multiply connected domain. Let's see why. We can have, well, here our domain is the unbounded domain. We can have 2 continua E and F that are big and they're close to each other, but we might have a very, very narrow passage between the boundary components of the domain. So this forces the modulus to go to 0, to be very small. Okay. Even if these are just objects that have very nice geometry, there are round disks, for example, this could happen. The passage here could be very narrow, so the modulus goes to 0. So we do not have the Loevner property for multiply connected domains, even when we have very nice geometry. But the rest of the argument actually works. I mean, we have quasi-conformal invariance. It's still true for multiply connected domains, and we still have the same upper bound for modulus of annuli. So it's only the Loevner property that fails. We have to fix this first, and here comes the transboundary modulus of Schramm. So Schramm in 1994 invented transboundary modulus with respect to a given domain, and he used it to give a proof of Koeber's conjecture in the countably connected case. So it was a major result at the time. As I said, since then it has been used in numerous works in complex analysis. Now, transboundary modulus is another outer measure on curve families. I'm not going to give the formal definition, but it still enjoys conformal invariance. And the great advantage is that it can measure the size of families of curves that go outside the domain. So it gives a number to the size of those curve families. So in the previous example, in the left picture, the classical conformal modulus was very small because of a narrow passage. But, well, transboundary modulus says you don't have to stay in the domain. We can also look at the curves that go through the boundary components. And because of that, the transboundary modulus is large in the right picture. So it turns out that actually, if we use transboundary modulus, then the Leibniz property is true. Specifically, if omega is a domain in the sphere and the complement consists of closed quasidisks, they're uniform quasidisks, then we have the Leibniz property, which means that if the relative distance is bounded above, then the transboundary modulus with respect to the domain is bounded from below. Now, this Leibniz property was proved first by Mario under the additional assumption of relative separation. But later, this assumption was removed in work of Hrant Jacobian and Wen Bo Lee. And also in my paper, I have an even more general version of this Leibniz property. So this is fine, the first part of the argument. We can use transboundary modulus. Let's continue with the rest of the argument. We still have conformal invariance and quasi-conformal quasi-invariance. So the second part of the argument works. So if we take the transboundary modulus with respect to the image domain, this is the same as the original transboundary modulus. And then we have to try to prove the final step, which is like the reverse Leibniz property. But unfortunately, this fails again. We can have a picture like this. We can have continua E prime and F prime that are small and they are far from each other, so the relative distance is large, but the transboundary modulus is large as well. This can happen when we have a large disk which is close to both of the continua, so it functions as a bridge. So the idea is that we can kind of erase this disk and bring the continua E prime and F prime close to each other. So that's how transboundary modulus behaves in this case. But the problem is caused by those bridges that are large disks that are close to both E prime and F prime. Well, Mario had the great idea to fix this problem by avoiding the bridges. So he proved that there is a uniformly bounded number of bridges, in fact, at most 2. And by avoiding these 2 bridges, we can get the desired estimate. So instead of looking at this curve family that goes through this big disk, we just avoid the disk, and we look at the curve family that only goes through the other complementary disks. And well, if we avoid the bridges, so we define a new domain, it's the sphere minus the bridges, then we get the desired implication that whenever the transboundary modulus is large, but of course we avoid the bridges, if any, then the relative distance must be small. So it seems to have an easy fix by just restricting the curve family and getting what we want. But well, now this causes another problem, that when you make the curve family smaller, you might destroy the Leibniz property. Remember this phenomenon? Well, in order to ensure that this modulus was large, we wanted to be able to use curves that travel through the boundary components. But well, if you cannot do this, then we're back to the same problem of narrow passages. And again, Mario has the clever idea here that we can use the uniform relative separation condition to guarantee that the Leibniz property still holds when we avoid a bounded number of quasidisks. So if we have the uniform relative separation, there is enough space between these 2 disks so that the Leibniz property is still true. Okay, and so far I just completed the presentation of Mario's proof. Now, how can we deal without this assumption? Okay, how can we replace this assumption with condition C, the circularization assumption? So I remind you that our goal is to show that whenever the relative distance is bounded above, then the images have the same property. So let's suppose, for the sake of contradiction, that this doesn't happen. So the relative distance of the images is large, and there exist, as I said, at most two bridges, which means there exist at most two large disks that are close to both E prime and F prime. Of course, here one has to define formally what it means to have bridges, and this is not easy actually, but for the sake of the presentation, we mean large disks that are close to both sets. So somehow we have detected the two problematic disks. The smaller disks are not a problem. Of course, there might be many more other disks that are not a problem. And here we have the conformal map F that maps these quasi-disks to the disks. So we have detected these two possibly problematic quasi-disks. And here we apply our circularization assumption. So we map those two disks, quasi-disks, to round disks. Okay, our assumption was that any pair of quasi-disks can be mapped to a pair of round disks with a quasi-conformal map of the sphere. All right, so we apply our assumption. Now these other regions UI, they will become some other quasi-disks. They're not going to be circles. There will be some other quasi-disks. Since quasi-conformal maps behave nicely, they have nice geometric properties, it suffices to just focus on the right picture and prove this implication that, well, whenever h of E and h of F have bounded relative distance, the same happens for the images. Okay, so we just focus on the right side of the picture. Again, this is what we have to show. And this is just the right side of the picture, just flipped. Now, what we do is we take this map G, which is the composition of the maps of the previous slide. It's the right side of the picture. And we extend it by reflections. Okay, we have two disks getting mapped to two disks, so we can reflect. And we get this. So we can extend the map G to a larger domain. The map is going to be quasi-conformal in the white part of the picture, and also it's quasi-conformal on this circle because circles are removable for quasi-conformal maps. And then we reflect again, and we do this again, and we do this indefinitely. So in this way, we have extended the map G to a bigger domain. All these dotted circles are removable for quasi-conformal maps. So the new domain has a complement that consists of these sets VI and the reflections and the limit points here. Okay, so this is our domain. Now let's make some remarks about this extension process. First, the reflections of VI, they are still uniform quasi-disks because reflections are Mobius transformations, so they will preserve the property of being a quasi-disk. And therefore, in this new domain, we have the Leibniz property for transboundary modulus. Remember, as I said, the Leibniz property is true if the complement consists of quasi-disks. So on the domain side, everything is fine. Now on the target side, initially we had two problematic disks, Ki1 and Ki2. The other disks were good. They were favorable. So they would not cause any problems in modulus computations. We have to ensure that those reflections, they still remain favorable. They don't cause any new problems. This, based on the picture, looks easy because reflections make disks smaller, but again, it's something technical that has to be ensured. So the reflections of those disks are favorable. They do not create any new bridges between E prime and F prime. And the two problematic disks, they have now disappeared. In the limit, they have become these 2 points. So therefore, there's no problem with running the previous argument. So let's try to run the argument now. We start with the two continua, h of E, h of F, having a bounded relative distance. We apply the Leibniz property in the left side So we can get a modulus bound, a lower modulus bound. We apply the quasiconformal invariance of modulus. So we get a lower bound for the modulus of the images. And then, since we have eliminated the bridges between E prime and F prime, we can actually show that there is a certain upper modulus bound for annuli. So here we consider a certain annulus that separates E and F, E prime and F prime, and we prove that the modulus satisfies this inequality. So if we compare this to the modulus of the classical case, to the toy version, in the right side we had 2 pi log r over r to the -1. Okay. So here there's some other function psi, which is a decreasing homeomorphism and does exactly the same job. So because we have this upper modulus bound, we have all the 3 ingredients that we need, and we can show that the relative distance of E prime and F prime is bounded above. So this completes the proof of the existence. I have one slide with the uniqueness. I don't know if I need about 3 to 4 minutes, if it's fine.
Yeah, you still have time.
Okay, so let's say a few words about the uniqueness. So let's suppose here that we have our set S, and we have 2 quasiconformal maps that transform them to 2 Schottky sets, T and T tilde. And both maps are 1 quasiconformal on S. So we want to take the composition of F tilde with F inverse and show that it is a Mobius transformation when restricted to the Schottky sets. So this is the uniqueness statement. So we want to extend the map G by reflections to a quasiconformal homeomorphism of the whole sphere. And this is now, I would say, a standard argument. Well, it's a bit hard since we have infinitely many disks. In the picture, we only see finitely many. This is how it's done. Of course, we take a point Z inside a white disk. We reflect it outside. We map it over by G, and then we reflect back inside. So in this way, we have extended G to the reflection of the Schottky set. And we can do the same to the other disks as well. So we have extended the map G to a bigger Schottky set. And we can continue doing the same process in every disk. So in the limit, we will get a homeomorphism of the sphere. It turns out that this homeomorphism will be quasiconformal. And this actually, the details of this argument have been proved by Mario and Sergei Merenkov and Bruce Kleiner. So they have a paper about the rigidity of Schottky sets. So now what are the properties of this map? First, we can show that it is 1 quasiconformal on the buried points. These are the points that lie in infinite intersections of nested white disks. So why is it 1 quasiconformal? Well, the map is differentiable almost everywhere. So it's differentiable at almost every such point because it's quasiconformal, and it maps those infinitesimal white disks to infinitesimal white disks. So that's why it's going to be 1 quasiconformal. And on the pink set, by assumption, the map is 1 quasiconformal on the pink set S. And it's also 1 quasiconformal on the reflections, because we just compose it with Mobius transformations. So it is 1 quasiconformal also on the Schottky sets T and on the reflections. So altogether, the map is 1 quasiconformal at almost every point of the sphere. It is quasiconformal in the entire sphere. So we can apply Weyl's lemma to prove that it's a Mobius transformation. All right, so this is the end of my talk. Thank you very much for your attention.
Yeah, so let's thank Dimitrios. Super clear talk. Yeah, any comments or questions? Can we go back to the 1 quasiconformality of your map? You didn't say anything about this, right? Let me just make sure that I understand this correctly. I mean, in the existence part, right? So, I mean, you get the map as
yes, I didn't say anything. Correct. Yes.
I mean, you get the map as the limit of conformal maps, right?
Exactly, it's the limit of conformal maps, and there's lower semi-continuity on the K when you have K quasi-conformal maps, Kn quasi-conformal maps. When you have there's lower semi-continuity under of the dilatation under uniform convergence. This is the result of Gehring and.
Yeah, I'm a little bit confused. I mean, usually, we just say things almost everywhere, but if you set as measure zero, I mean, what is the
Oh,
condition?
yeah, it's vacuously true. Yeah, if it has measure zero, then it doesn't say anything.
I
Yes.
see, I see, I see. It's only if the measure, if you have positive measure, then you get a
Yes. And of course, in the case of area zero, you know very well that we get rigidity.
yeah, yeah,
So
yeah,
without any assumption about
yeah,
one quasi-conformality.
yeah. Well, so the question arises: how do what's the right condition for this pairwise for your condition C, right? I mean,
Yes. I think okay, there is some motivation coming from dynamics, and actually this theorem was motivated from dynamics. So I think the next thing to try is to understand exactly what happens in dynamics, perhaps why this parabolic basins they can be converted to tangent disks. That would be. I'm working with that problem, so hopefully there will be some progress.
maybe another question that maybe I didn't understand something correctly. I mean, suppose you have something like, I don't know, three triangles that have a common vertex, right?
Yes.
I mean, isn't the condition then true? Right, right. Every pair seems to be fine. So,
Well, but every pair, well, this pair cannot be converted to tangent disks
oh, I
quasi-conformally.
see, I see. So that's again your previous argument, right? Well,
Yeah, it's because of angles.
yeah, right. I see, I see, I see. Yeah,
Uh, yeah, basically the idea is that if you have two tangent disks, then you cannot fit a quasi-disk there.
yeah, yeah, I see, I see, I see. Okay. All right. So I asked my question. Does anybody else have comments or questions?
So is there some I don't know dynamic? I mean, so you have this pairwise I don't know circularizable thing, right? So I don't know. Is there like a dynamical I don't know interpretation of this, or conversely, is there something you have this sort of I don't know maybe almost interlaced Schottky sets or what? Is there some sort of operation where you take such things and sort of put them together to get these pairwise circularizable uh, sets? I mean, it's kind of an ill-defined question, but uh,
Maybe if I go to this slide,
yeah,
maybe.
yeah,
So are you suggesting that we look separately at the green and the red ones, or?
right, yeah, 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 yeah. So I mean, is there like, I mean, in a sense, it looks very intriguing that you have two Schottky sets and they're sort of put together in such a way. So is there like, I mean, some operation that you take two Schottky sets and sort of, I don't know, interlace them in a certain way to get these things? And is there some sort of operation that would, be behind this whole thing, especially in the dynamical setting or maybe also in the non-dynamical setting, but uh,
I mean, this sounds very reasonable in the dynamical setting because
yeah,
you need some dynamics to do this, some self-similarity maybe, but it's very
yeah.
interesting. You see it in the
I mean,
picture.
it's not a well-defined question, but it sort of looks very intriguing that you have these sort of two interlaced, and whether there's some I don't know precise procedure behind this operation or what
Yeah,
yeah,
people in dynamics do matings, so who knows? Maybe there's some
yeah,
mating process that does this, right?
So in this example, I mean, very naively, one could maybe first uniformize the green guys, right? Because as you said, they're
Mhm.
uniformly relatively separated. I guess then, the red guys remain uniformly relatively separated. Now one could take this picture and make the red guys circles and, keep going back and forth and,
Yes.
could speculate whether this procedure somehow converges.
I mean, that was actually my initial approach. This is like Goluzin's proof of
Yeah, exactly right. There's
optimizations.
exactly.
But there's no way to control the quasi-conformality constant.
Yeah, one would
Wasn't
think. I mean that they somehow get closer and closer to one or something like this.
I
Actually,
mean, topological, yeah. Yes.
this I was actually looking for a reference of this procedure. Is this in Goluzin's book, or where is this? What you just mentioned?
Probably. Yeah, I'm not, probably it is, but I don't remember.
Yeah, okay. All right. Other comments or questions? Well, then let's.
I have a,
Okay.
oh, sorry. I had a quick question about condition. I was wondering if you had an additional example of when the pairwise circularizability like failed. So you mentioned with the squares meeting at the vertices or with the triangles,
Mhm.
because you have like a non-zero angle there, and on the circles you kind of have like a zero angle. Do you
Yeah,
have an
so
example?
okay, I can say just I'm trying to work out some examples now. And okay, if we have, I mean, instead of looking at tangent disks, one can look at parallel lines. Okay, find the condition so that so that two topological lines are quasi-conformally to parallel lines. Okay, this is equivalent. So if one of them is the, let's say, straight line, if one of them, let me erase. Then if, let's say the other one is a graph of a function. So if a function is like, if it's a power function, then it can be quasi-conformally transformed based on the computations I did if they are correct. If it's exponential, then no. Okay, so of course this is not a surprise, but even these examples are not easy to work out.